In physics and mathematics, in the area of dynamical systems, a double pendulum is a pendulum with another pendulum attached to its end, and is a simple physical system that exhibits rich dynamic behavior with a strong sensitivity to initial conditions. The motion of a double pendulum is governed by a set of coupled ordinary differential equations. For certain energies its motion is chaotic. Analysis and interpretation. Several variants of the double pendulum may be considered. The two limbs may be of equal or unequal lengths and masses, they may be simple pendulums or compound pendulums, and the motion may be in 3 dimensions or restricted to the vertical plane. In the following analysis, the limbs are taken to be identical compound pendulums of length and mass, and the motion is restricted to 2 dimensions. In a compound pendulum, the mass is distributed along its length. If the mass is evenly distributed, then the center of mass of each limb is at its midpoint, and the limb has a moment of inertia of about that point. It is convenient to use the angles between each limb and the vertical as the generalized coordinates defining the configuration of the system. These angles are denoted I1 and I2. The position of the center of mass of each rod may be written in terms of these 2 coordinates. If the origin of the Cartesian coordinate system is taken to be at the point of suspension of the first pendulum, then the center of mass of this pendulum is at, and the center of mass of the second pendulum is at. This is enough information to write out the Lagrangian. Lagrangian equals, the Lagrangian is. The first term is the linear kinetic energy of the center of mass of the bodies, and the second term is the rotational kinetic energy around the center of mass of each rod. The last term is the potential energy of the bodies in a uniform gravitational field. The dot notation indicates the time derivative of the variable in question. Substituting the coordinates above and rearranging the equation gives. There is only one conserved quantity, and no conserved momenta. The 2 momenta may be written as and. These expressions may be inverted to get and. The remaining equations of motion are written as and. These last 4 equations are explicit formulae for the time evolution of the system given its current state. It is not possible to go further and integrate these equations analytically, to get formulae for I1 and I2 as functions of time. It is however possible to perform this integration numerically using the Runge-Kutta method or similar techniques. Chaotic motion. The double pendulum undergoes chaotic motion, and shows a sensitive dependence on initial conditions. The image to the right showed the amount of elapsed time before the pendulum flips over, as a function of initial conditions. Here, the initial value of I1 ranges along the x direction, from A3 to 3. The initial value I2 ranges along the y direction, from A3 to 3. The color of each pixel indicates whether either pendulum flips within, or initial conditions that don't lead to a flip within are plotted white. The boundary of the central white region is defined in part by energy conservation with the following curve. Within the region defined by this curve, that is if. Then it is energetically impossible for either pendulum to flip. Outside this region, the pendulum can flip, but it is a complex question to determine when it will flip. Similar behavior is observed for a double pendulum composed of 2-point masses rather than 2 rods with distributed mass. The lack of a natural excitation frequency has led to the use of double pendulum systems in seismic resistance designs in buildings, where the building itself is the primary inverted pendulum, and a secondary mass is connected to complete the double pendulum. See also, double inverted pendulum. Mid-20th century physics textbooks use the term double pendulum to mean a single bob suspended from a string which is in turn suspended from a V-shaped string. This type of pendulum, which produces Lissajous curves, is now referred to as a Blackburn pendulum. Notes. References: Myrovich, Leonard. Elements of Vibration Analyses. McGraw-Hill Science Math. ISBN 0-07-041342-8. Eric W. Wellerstein, Double Pendulum, Science World and Double Pendulum by Rob Morris, Wolfram Demonstrations Project, 2007. Peter Lynch, Double Pendulum. Northwestern University, Double pendulum, theoretical high-energy astrophysics group at UBC, double pendulum. External links, animations and explanations of a double pendulum and a physical double pendulum by Mike Wheatland, interactive JavaScript simulation of a double pendulum physics simulation from www.myphysicslab.com, simulation, equations and explanation of Roth's pendulum, comparison videos of a double pendulum with the same initial starting conditions on YouTube, double pendulum simulator, an open-source simulator written in C++ using the Qt toolkit. Online Java simulator of the imaginary exhibition. Free simulator app. 2 double pendulums side by side, watch divergence of close initial conditions / see periodic orbits.